Hello, algebra friends. So this lesson is a fairly short intro into the basics of probability. So probability is one of those concepts that, they touch on in younger grades and maybe you've picked up on a little bit as you've just, gone around your own life. They talk about probability quite often in the news. They don't always display it the same way though. And then what we found out a few years ago is that, my face is really in the way here. You guys may or may not be familiar with just what's a deck of playing cards, like a traditional deck of playing cards. So first thing to note, and you can look up this image on the internet, obviously, on your own, but there are a total of 52, if you're not including the jokers, in the deck of playing cards. My pen's not working. There we go. Oh my gosh. Total, there we go. Total of 52. And they're broken up into what we call suits. So the suits are, right here we have the clubs. And you'll notice all of the clubs are black in color. And ace, high or low, doesn't matter. But there's an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then jack, queen, king would be the additional cards. So there are 13 clubs. And the next suit is called the spades. Also black, look like little shovels, and there are 13 of those as well. And then we have the hearts, which are all red, and there's 13. And then the diamonds. So 13 red diamonds, 13 red hearts, 13 black spades, and 13 black clubs, totaling to 52 playing cards. If they ever reference something in a problem called like a face card, that's literally something with a face. So a jack, a queen, and a king would be face cards. Don't get hung up on like, is ace high or low and which card is worth more. We're not playing games with these cards today. We're calculating what are called simple probabilities. So we'll make sure we post a visual of a deck of playing cards in case you run into those in your questions in the future. But some of you grew up playing with playing cards, so you know a lot about them, and some of you have really never seen a deck of playing cards. So I wanted to give you a little rundown on that. So these probability questions, the first thing we have to come up with is what's the definition of like a probability? So it's the number of favorable outcomes divided by the total. Number of total outcomes. So I'm going to win versus how many times the game is played, I guess is a way to think of it. So in this basic probability question, we're going to pull one card out of a deck of cards like a magician would without looking. So what's the probability that you would pull out a red playing card? Well, if you remember, there was the two suits, right? So there's 26. Oops, I'm using the wrong, well, whatever, red's fine. Out of the total, remember there's a total of 52 playing cards. And then if you math enter that on your calculator or just kind of thought logically about this comes out to a probability of 1/2. So it's an equally likely chance of pulling out a black card or a red card in a standard deck of playing cards. Now, the other way they might express the probability here is as a decimal. So they might say 0.5. It doesn't matter. They also could say a percent, I suppose. So 50%. It depends on like who your audience is. People in the news don't like to see fractions when you're displaying probabilities. They much prefer percents, sometimes decimals. But you have to know your audience, I guess. All right, so the probability of pulling out a heart. So remember the heart, that's one full suit. So some of you already can logically see the spatiality of it. But there are 13 hearts in the deck of 52 cards. And if you were to math enter that on your calculator, that would come out to a fraction of 1/4. Now, when I think about that logically, yeah, that makes a lot of sense because the heart is 1 out of 4 of the suits, so 1/4. Again, you could write that as a decimal or even as a percent. It's whatever the audience wants. All right, a red 7. So maybe we'll go back and look at the deck of cards real quick. A red 7, well, there's 2 red 7s right here, right? There's the 7 of hearts and 7 of diamonds. So there's, how many winners were there? There's 2 out of the total 52. And again, math enter on our calculator, that reduces to a 1/26. And I don't really know what that is off the top of my head as far as reducing the fraction to or rewriting it as a decimal. So fraction works for me because you're my audience and you don't care, right? All right, the next one's a bit of a trick question. Black heart. Well, remember, the heart suit is all red, so there is a 0 out of 52 chance of that happening, which means there's a 0% probability, or just 0. So there's going to be words coming up in your Delta math practice where it says, like, is this event unlikely, certain? In this case, this event here would be what we call, I'm going to write this in a different color so it stands out. This is impossible. Good job, mathematicians, thinking of a clever word for impossible. A red 7 is a 1 out of 26 chance. If we converted that to a decimal, it's pretty small. It's like, I'm going to say 4%-ish. Okay, so it's unlikely would be a word they might describe. I'm always impressed with people who can calculate things really fast in their head for like a useful purpose. Like poker players are amazing at understanding what's in the playing card deck, what's the likelihood of something happening. And then here, I forget, I'm going to wait for the Delta math lesson. We're going to do a little bit together on this, but it's like an even split, right? Pulling a black card versus a red card on a full deck is, you know, it's not that it's likely or unlikely. It's just kind of, it's even between the two of them. Some people would claim a 25% is unlikely. Delta math is going to go through some very obvious cases, right? They're not going to give you things that like are questionable. You know, if you have a 3% chance of something happening, that's unlikely. If you have a 98% chance of something happening, that is likely to certain. We might call that certain. But, you know, something like 80% chance, like that's likely. Okay, don't overthink them. Sometimes we overthink them as humans. All right, this cracks me up because I see this on not so much the SAT test, but on the ACT test back in the day. They used to call things a six-sided number cube. Well, to most humans, they're like, you mean a die? Yeah. So they don't want to call it a die or a pair of dice because that is a term used mainly by Americans. And, you know, the traditional die that we think of is six-sided, but any gamer out there will tell you there's a lot more types of die out there. Some D&D fans out there. So they have to claim exactly what kind of dice we're looking at. So in this case, it's a traditional six-sided number cube. So what's the probability of rolling each of these things? All right, so what I'm going to do first is I'm going to write what's called the sample space. It kind of says sample. So the sample space would be you're either going to roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And if I could draw, I'd actually draw that out. So one of those 6 things is going to happen. So my denominator, the total number of possible outcomes, is going to be a 6 on each of these fractions for probability. Come on, pen. Oh my gosh. This is not my day for pens to work. But would it really be an Abruzzo lesson if my pen worked? No. Okay. So the probability of you rolling a 4, well, that's 1, right? 1 out of the 6 outcomes. An even number, though, be careful here, even number would be a 2, a 4, or a 6. So in that case, you would have a 3 out of 6 probability, which of course we would reduce to a 1/2. So this is one of those equally likely outcomes, even versus odd on a six-sided number cube. You know, one's not better than the other for probability. A number greater than 1. Now watch the vocab here. Greater than 1 mean not 1, but everything bigger than 1. So that would be a 5 out of the 6. That's a very likely outcome. But, you know, I think we've all played a game where like, okay, anything but a 1, and then you roll it and you're like, a 1 went. All right, and then a probability of rolling a 7. Well, y'all, there's not a 7 on a six-sided number cube, so that is a impossible probability. It will not happen. Okay, I guess I should box in these answers. It looks a little less ugly. Notice I didn't change any of those to decimals or percents because I'm lazy, mainly. All right, so here we have a Bill, John, Sue, and Bob. So these 4 people are all up for a job promotion. The boss is going to choose, a team of 2 to lead the department. Everyone's equally likely to get the position. Sure. All right, show the combinations for the team. So this word here, combination, is actually a different word in probability land. Don't get hung up on that notation. We're just going to talk about what right now we know is the sample space. So the sample space would be all of the possible outcomes, right? So this one's a little more complicated. I have to like list them out. So good news, there's not too many people involved here. So it could be Bill and John. And I like to do this a little systematically, otherwise I get confused. It could be Bill and Sue. And it could be Bill and Bob. Now, that's all the combinations that include Bill. So get out of there, Bill. Because I don't want to say John and Bill, because that's the same team as Bill and John. So now I could have John and Sue. Oops. And then John and Bob. And then again, John's out of there now. That's all the combinations for John. And then Sue and Bob. And notice I didn't bother reversing any of these because that would be the same team. Those of you who are familiar with the word combination versus permutation, this is a clear case of a combination, not a permutation. So the probability, notice there's 1, 2, 3, 4, 5, 6 possible outcomes. Those of you who did the combination on your calculator or formula, you did 4 choose 2, and you got 6 possible outcomes as well. So my probabilities, which I didn't leave myself much space here, are all going to have denominators of 6. So Bill and Sue get the promotion. There's only one team out there that has Bill and Sue as the team. So that's 1 out of the 6. So that's the probability of that happening. And then the other question, and this notation, I don't think I covered this very well in the last slides, P and then parentheses is a way of saying what is the probability of this event occurring. So here, Bob is one of the people getting a promotion. So where does Bob fall in? So here's Bob, and here are Bob. So 3 out of the 6 teams, which of course we'd reduce to a 1/2. So Bob has a 50% chance of being on the team. And you know what, fun fact, so does everyone else. So I guess if Bob really wanted to be teamed up with, you know, one of the people, he'd have to look at that probability separately. All right, so let's take a look at some probability rules. This comes up a lot on our Delta math practice. The good news is a lot of this is kind of, I don't want to say second nature to you, but like you have a little familiarity with how probability works in real life because you've seen it. So the probability of an event occurring is notated by this notation, okay? That's all that means. P and then parentheses, whatever's in the parentheses is the event. So it could be like symbols from math. It could be something more complicated in the future, you know, when you take some other math classes, and it's very likely for our class is going to be a short sentence fragment. You know, us math people, we don't like to write. So this is a very important rule that seems logically based, but for some reason people forget it. The probability of an event occurring has to be between 0 and 1. Well, I should say including 0 and 1. So remember, we saw those impossible events where the probability was 0, and then we haven't seen this yet, but there are certain events, we call them, where the probability is 100%. Like, I don't know why I can't like think right now, but you know, what is the probability that I'm going to mess up in a lesson? Like for me, that's like 100%, right? That's a bad example. But what is the probability? Like today, for instance, the weather, when I look outside and look at my phone app, probability that it's going to snow today was 100%. So there is no chance that it is not going to snow. How much snow? I don't know. We'll see. All right. The sum of the probabilities of the entire sample space has to add up to 100%. So for instance, that rolling the 6-sided number cube. If I have a 1/6 chance of rolling a 1 or a 2 or a 3 or 4 or 5 or 6, if I were to add up all those probabilities, 1/6 added together 6 times equals 100%. A sample space covers every possible outcome with no exceptions. That's what a sample space is. And then this one is interesting. It's called the complement. And this doesn't show up so much on the SAT test as far as vocabulary, but the concept shows up. So if you want to know the probability of an event not occurring, just take the simple formula of 1 minus the probability of an event occurring. So for instance, tomorrow there is a 30% chance of snow. So that means there's a 70% chance of no snow. So which one's more likely? I guess no snow, but you know, they've been wrong before. So this example here is straight off of an old ACT test. And it says the probability of an event occurring is 3/5. What's the probability of the event not occurring? So in college prob and stats classes, they do this all the time where they give you no context to the problems and then just say like, figure it out, kid. So we know from the complement rule of it not occurring would be 1 minus the 3/5. Now, those of you working without a calculator, this isn't that hard, guys, right? This is really a 5/5 minus 3/5. So the complement to that would be a 2/5. Again, you could, right now, you could type on your calculator, but 3/5, so 3 out of the 5 times it occurs, that means 2 out of the 5 times it would not occur. So these aren't very exciting if they don't have context to them, the problems, but, you know, whatever. Calculations are easy enough. Speaking of calculations, what if you have multiple events? Well, right now, these next two examples are called independent events. They don't affect each other. But the idea is you just simply multiply them together. That's it. So when I look at this question, it says we're going to roll a die, I never get that right, and we're going to flip a coin. They have nothing to do with each other. So flipping tails on a coin has nothing to do with the outcome of the die. So what is the probability that you will roll a 5, and then you're going to flip the coin and it's going to land on tails? So rolling a 5, remember the sample space on a 6-sided die, let's assume there's 1 out of 6 outcomes where it's going to be a 5, right? Because it could be a 1, a 2, a 3, a 4, a 5, or a 6. And then for coins, we're not going to think about like the weird example of it falling on its side because it's a trick coin, but heads and tails, that's it, 50-50 shot. So for a coin to flip and land on tail, that would be a 1 out of 2, or a half. And then according to this rule here, we just simply multiply them together. So if I multiply these fractions together, you really just multiply the numerators and denominators together. So you get a 1 out of 12. Interesting. All right, so now we're going to roll a pair of dice. What's the probability that you're going to roll a pair of 3s? So I know they're the same thing, but they're not the same die, like two independent die here. And even if it was the same die rolling twice, it still wouldn't matter. So what's the probability that I'm going to roll a 3 and then another 3? Well, again, the die could be a 1, a 2, a 3, a 4, a 5, or a 6. So rolling a 3 is a 1 out of 6 on the first die, and then we multiply that by another 1 out of 6. So there is a 1 out of 36 chance that you will roll the die and you get a pair of 3s. Interesting. So, by the way, that is an unlikely event. Any of you who are out there playing games with each other. Unlikely. All right, this one is always a little depressing. We have 2 tests. We have test A and test B. So here's test A. The chance of you passing it is 40%. Okay. So then there's test B. Even worse. The chance of you passing test B is 20%. These are independent of each other. Okay. So test A. Let's think about this for a minute. I'm going to pass, and instead of rating it as 40%, I'm going to rate it as 0.4. Pass it, 0.4. Now, for fail, think about the complement rule. That means you're going to fail at 60%, so 0.6. Yikes. And then for test B, you're only going to pass at 20%. That's horrible. Unless this is one of those weird tests you don't want to pass. And then you're going to fail at 80%. So I'm going to call that 0.8. Yikes. Okay. So look at these two probabilities, and we're just going to multiply them together. So if we're going to fail A, so that would be this guy here, so 0.6. And then we're going to fail B, which is 0.8. And we multiply these together, you're going to get 0.48. So almost 50% of you failing both tests. All right, so then passing A would be 0.4, and then failing B would be 0.8, and if we were to multiply these together, we would get a 0.32, like 32%. Okay. What about failing A? So that would be a 0.6, but passing B, that would be a 0.2. So if I multiply those together, I end up with 0.12, so like 12%. Yikes. Okay. And then passing both. So if I passed A, that's a 40%, and passing B is a 20%. Watch your decimal points here, guys. If you multiply these on the calculator, it'll spit out the right answer, but this is 0.088%. So most likely outcome is that we fail both tests, and the least likely outcome is that we pass both the tests. Isn't that always the case, man? All right, so notice something. If we were to add all of these together on our calculator or in our head, if you added up all of these, and this is called the sample space, right? All the possible outcomes. Woo! That was supposed to be an S. All right, sample space. If I added up the whole sample space probabilities, they add up to 1 or 100%, which is what's supposed to happen, right? If you add up all the probabilities of the sample space. So that was an interesting piece of data. I don't really know the context to it. Hopefully it's the kind of test you don't want to pass. I can't really think of a test that I want to not pass, but whatever. All right, so those were all independent events. What if the events are dependent on each other? So the most common showing problem that we see is, and this is a deck of cards, but usually it's like marbles in a jar or jelly beans, or, you know, you're going to pull one thing out of the jar and then remove it from the problem. So then when you reach in the second time, you have less things in the jar, or in this case, cards in the deck, and it shifts the probability because there's less possible outcomes. So this happens a lot when you're playing a card game like poker or blackjack. So the dealer is dealing out cards, and if they're only working with one deck, it's a little easier to manage, but usually they work with multiple decks. So the probability of you know, getting that ace that you need is higher early on in the game than as you move through the game. So as cards keep getting dealt out, and you know what you have in your hand, and you see what's on the table, possibly, depending on what kind of poker you're playing, the probability of you getting that ace on the next pull, on the next pull, on the next pull, it keeps changing. So I'm really impressed by people who have the capability to do that in their head. I think that's amazing. I know I can't. All right, so if you have a deck of cards, a standard deck of playing cards, what's the probability that you will pull 2 aces in a row? So we have our 2 events, and we know we're going to still multiply them together. But watch the probabilities here, guys. So for aces, you have aces of all of the suits, right? So at the first pull, you're going to have 4 out of 52. Okay? So let's say magically I reached in, I pulled out a card, and aha, it was an ace. So let's say it was the ace of diamonds. I don't know, I'm making that up. And I put it on the table over here. And then I reach in again. Now the next time that I go to reach in, I already took out one of the aces, and I also inherently took out one of the total number of cards, right? So this 4 now becomes a 3, and the 52 is now a 51. So these can get tricky because you got to watch. Sometimes the numerator and the denominator changes, and sometimes it's just the denominator that changes. You know, you got to read the question very carefully. And of course, I'm supposed to be able to do this in my head, right? Now, all right, so let's see, I should be able to do this quickly on my calculator, huh? So the fraction this comes out to is 1 out of 221, and the decimal equivalent to that is 0.0045. So really, really, really tiny probability. And that's just one deck of playing cards, right? Usually we talked about this when they're playing like actual poker in a casino or something, they have multiple decks. So if I wrote that as a percentage, it'd be 0.45%. Tiny, tiny number, like not even 1%, not even 0.5%. So the chances of you pulling out an ace from just a single deck of playing cards, incredibly small, like almost impossible. Very unlikely, I guess would be the best way to describe that. Okay, so on Delta Math for your practice, if it's, you know, maybe I changed it up a little bit, but what I'm planning on assigning is several assignments on probability, and you want to make sure you do them in order. So the first probability assignment is all about vocabulary. You know, is this event likely, unlikely, certain, even? So that's the first probability assignment, and then it starts working into calculating basic probabilities like we saw here in this lesson. And then your third probability assignment has to do with what's called conditional probability, and that's actually in our next lesson. So good luck to everybody.